linear system of equations, and we'll see a method to solve a system of equations if it is consistent. Let me start with the definition of a linear equation. Any equation of the form a1x1 plus a2x2 plus an(xn) equal to b, where a1, a2, an and b are constants and x1, x2, xn are the unknowns. Any such equation where a1, a2, an and b are constants and x1, x2, xn are unknowns is called a linear equation. We call it a linear equation for obvious reasons because all the unknowns appear up to degree 1. There are no square terms, no square roots anywhere. There are no products of the unknowns. So all unknowns appear up to degree 1. Such an equation will be called a linear equation. And by a solution of such an equation, we mean a sequence S1, S2, Sn of numbers such that when I put x1 equal to s1, x2 equal to s2, xn equal to sn. When I put x1 equal to the first value, x2 equal to the second value, xn equal to the last value, this equation has to be satisfied. Then s1, s2, sn together, this will be called a solution of this equation. Now, what we are going to study is a group of such equations. So, we are going to study a linear system of equations. In general, we will consider n linear equations in n unknowns. So, our system would look like a11 x1 plus a12 x2 plus a1n xn equal to b1, a21 x1 plus a22 x2 plus a2n xn equal to b2, am1 x1 plus am2 x2 plus amn xn equal to bm. So in this system we have m equations and the unknowns are x1, x2, xn. Once again, we will say that a sequence s1, s2, sn is a solution of this system if and only if when I put x1 equal to s1, x2 equal to s2, xn equal to sn, each and every equation has to be satisfied. That means this should be a solution of all the equations in the system. So what we are looking for is a simultaneous solution for all these equations. Now there is a very convenient way of representing these equations, and that is using matrices. So in matrix form, the same information can be conveyed as Ax equal to B, where A stands for the coefficient matrix, which will be a11, a12, a1n, a21, a22, a2n, an1, an2, ann. So here A stands for the matrix of coefficients x equal to x1, x2, xn stands for the matrix of unknowns, and B equal to B1, B2, Bm stands for the matrix of constants that occur on the right hand side. So the same system of equations can be represented in matrix form as Ax equal to B, where A is the coefficient matrix, X is the matrix of unknowns, and B is the matrix of constants. Now let us at least give a geometric motivation as to what we can expect when we are looking for solutions of such a system. dy equal to c, dx plus ey equal to f. So just for the geometric motivation, I am taking a system with two equations, two unknowns. This is a system of linear equations. So if I represent this geometrically, each is an equation of first degree in x and y. So it's going to represent the line. Now if I am looking for a solution which will satisfy the first equation as well as the second equation, I am looking for a point x comma y which will lie on the first line also as well as on the second line. So what I am really looking for when I want a common solution is a point which lies on both the lines, that means a point of intersection. And we all know that when two lines intersect, there are three possibilities. One is, if the two lines are parallel, then they are not going to intersect at all. So, no point of intersection. Another possibility is something like this, where they have exactly one point of intersection, and the third possibility is that the two lines are identical. L1 is the same as L2, so they have infinitely many points in common. So when two lines intersect, there are only these three possible cases: no point of intersection, exactly one point of intersection, or infinitely many points of intersection. Notice that it will never be possible for two lines to intersect in exactly 4 points or exactly 5 points. That's simply not possible unless you have something like this. Then it would be possible. But then we are not looking at such figures, we are looking at lines. So for lines there can be only 3 possibilities. Either there will be no point of intersection, exactly one point of intersection, or infinitely many points of intersection. So for such a system, I'll get either no solution, exactly one solution, or infinitely many solutions. Now whatever happens for two equations in two unknowns, exactly the same result works for a linear system also. So for a linear system of equations, Ax equal to b, there are 3 possibilities. One is, the system is inconsistent, that is, it does not have a solution. So when I take a linear system of equations, one possibility is that it has no solution. A second possibility is that, of course, the second possibility is that it is consistent, and then I can further break this up. If it is consistent means it has a solution, and here there are 2 possibilities. If it has a solution, it will have exactly one solution, or it will have infinitely many solutions. So when we are looking at the question of solutions of a linear system, there are only 3 cases that will arise. Either the system will have no solution, or it will have a solution and exactly one solution, or it will have infinitely many solutions. The only case that is excluded is where it has exactly 2 solutions, or exactly 3 solutions, or exactly 4 solutions. That just cannot happen. So for a linear system, either it is inconsistent, it has exactly one solution, or it has infinitely many solutions. Now how does one know in which case the system will not have a solution, in which case it's going to have exactly one, and in which case it will have infinitely many solutions? There's a very good method of checking this. For this, we will be looking at the augmented matrix A bar B. That means we will augment the coefficient matrix by the column of constants. So in the coefficient matrix, I will add one column to the end containing the constants P1, P2, Pn. We find the rank of this matrix. Suppose the rank of this matrix is R dash. And in the after bringing the matrix to the echelon form, if the number of equations left is equal to the number of unknowns, then there is exactly one solution or there is a unique solution. And if the number of equations is less than the number of unknowns, then there will be infinitely many solutions. So, in order to check what kind of a solution it has, whether it is inconsistent or consistent, we need to know the rank of the augmented matrix and the rank of A. If the two are different, we can straight away say that such a system is inconsistent. However, if the two are equal and the rank is equal to the number of unknowns, then there is a unique solution. But if it is less than n, then there will be infinitely many solutions. So let's work out a problem on this type. Let's investigate for consistency of the following equations and, if possible, find the solution. Start with the system. X plus 2y plus z equal to 3, 2x plus 3y plus 2z equal to 5, 3x minus 5y plus 5z equal to 2, 3x plus 9y minus z equal to 4. So the question is whether the system is consistent or inconsistent. If it is consistent, does it have one solution or infinitely many solutions? And in that case, we need to find the solution or solutions. So we start with the augmented matrix. In the augmented matrix, we first have the coefficient matrix. The coefficient matrix will be 1, 2, 1. That will be the first row. In the second row, we have 2, 3, 2. In the next row, we have 3 minus 5, 5. In the last row, we have 3, 9, minus 1. This is the coefficient matrix, but we need to augment it with the matrix of constants. The constants are 3, 5, 2, 4. So we put this in the last column. And now we are going to reduce this matrix to an upper triangular matrix. And for that, I'll have to reduce this matrix to the echelon form. So as usual, the first step will be to get a leading one in this row. We already have a leading one in this position. I need zeros below that. So I need the transformations R2 minus 2R1, R3 minus 3R1 and R4 minus 3R1. So that way I'll get zeros in these three positions. It will be 3 minus 4 minus 1, 2 minus 2 0, 5 minus 6 minus 1. In the next row it is R3 minus 3R1. So minus 5 minus 6 minus 11, 5 minus 3 2, 2 minus 9 minus 7 and then R4 minus 3R1, 9 minus 6 3 minus 1 minus 3 is minus 4 and 4 minus 9, that will give us minus 5. Next, I need to bring a leading one in this position. So the best thing to do is to multiply the second row by minus 1. That way we change the signs throughout. And then we need to bring zeros below that. So I need zeros in these two positions. And as we have done in so many other problems, to bring zeros in these positions, I must now make use of the second row. So the transformation 1, 2, 1, 3. The first two rows remain as they are. And this will be 0, 0, 0, 0. This will remain 2 minus 4. And this is minus 7 plus 11. Minus 7 plus 11 will be 4. And minus 5 minus 3. That should give me minus 8. Next, I need a leading one in the third row. So for that, I'll have to divide the third row by 2. That will give me 1, 2, 1, 3, 0, 1, 0, 1, 0, 0, 1, 2, 0, 0, minus 4, minus 8. And then finally, to bring a 0 in this position, let me do R4 plus 4, R3. Make use of the third row at this stage. So 1, 2, 1, 3, 0, 1, 0, 1, 0, 0, 1, 2. And this is going to be 0, 0, 0. We have started off with the augmented matrix and we performed several transformations on this, and finally this is the echelon form of the augmented matrix. In the echelon form, the last row contains zeros only. So the number of non-zero rows is 3. Therefore the rank of the augmented matrix is 3. So this is how we get the rank of the augmented matrix. Now we need to get the rank of the coefficient matrix. And the good news is that we don't have to separately put in an effort to find the rank of the coefficient matrix. We can make use of this information itself to find out the rank of the matrix. See, what we need to do is, the last column corresponds to the constants. So if I ignore the last column, and now in the remaining matrix, this part is associated with the coefficient matrix. Ignore the last column and now count the number of non-zero rows. So in the rest of the matrix, the number of non-zero rows is still 3. That means the rank of A is 3. And the rank of the augmented matrix is equal to the rank of the coefficient matrix. Therefore, the system is consistent. At least I know that this system has a solution. Now the question is whether this system has one solution or infinitely many solutions. So look at the number of unknowns. If the rank n is the number of unknowns, in the system there are 3 unknowns x, y and z, and the rank is equal to the number of unknowns. That's why this system will have a unique solution. See, at the end there are 3 equations left. There are 3 equations left after reduction, and there are 3 unknowns. If number of equations after reduction is equal to number of unknowns, then it will always give us a unique solution. And now let us actually find this solution. So we go to the echelon form, and from here we are going to rewrite the system of equations. Remember, the first column corresponds to x, the next one is for y, the next one is for z, and the last column is for constants. So if I rewrite the system of equations from here, I get x plus 2y plus z equal to 3, then 0x plus 1y plus 0z, that means y equal to 1, and from the last equation I will get 1 times z equal to 2. Now the idea is to start with the last equation and go backwards. This method is called the method of back substitution. We start with the last equation that gives us the value of z. Then go to the previous equation. From there we will get the value of y. Now put these two values in the first equation and that will give us the value of x. So x will be x plus 2 plus 2 is 3. That means x will be equal to minus 1. So this system has a unique solution, which is x equal to minus 1, y equal to 1, z equal to 2. Let's try out some systems which don't have a solution or in which we get infinitely many solutions. Let's try out the next system. 3y plus 7z equal to 5. 3x plus y minus 3z equal to 13. 2x plus 19y minus 14z equal to 32. And this time I'll quickly run through the echelon form. So let's start with the augmented matrix. Coefficient matrix is 2 minus 3 7, 3 1 minus 3, 2 19 minus 14, and augmented will have an extra column 5 13 32. Now let's reduce this to the echelon form. I can do R1 minus R2, that will give me 1, minus 3 plus minus 1 is minus 4, 7 plus 3 will be 10, 5 minus 13 will be minus 8. Then the first one should be minus 1, 3, 1, minus 3, 13, 2, 19, minus 14, 32. And now I am going to do a little bit of cheating over here. I need minus R1, so I will change the elements here itself. I want to change the sign of the elements in the first row. That should be done in a separate transformation, but to save some time, let me make the change here itself. So this will be the transformed row. Now let me bring zeros below that. So I need R2 minus 3 R1, R3 minus 2 R1. So I'll get 1 0 0 4 minus 10 8. Then 1 minus 12 minus 11 minus 3 plus 30 is 27, and 13 minus 24 is minus 11. Then we have 19 minus 8 11 minus 14 plus 20. Minus 14 plus 20 is 6, and 32 minus 16. 32 minus 16 is 16. Next, we need to bring the leading one in the second row. So let me divide the second row by minus 11. So we will have 1 4 minus 10 8 0 1 minus 27 by 11 1 0 11 6 and 16. Now we need a 0 below that. So I'll have to do R3 minus 11 R2, 1 4 minus 10 8 0 1 minus 27 by 11 1 0 0. This will be 6 minus 11 into minus 27 by 11. So this cancels. This will be 6 plus 27 33, and 16 minus 11. 16 minus 11 will be 5. Then let me divide the third row by 33. So I will get 1 4 minus 10 8 0 1 minus 27 by 11 1 0 0 1 5 by 33. Once again, look at the rank of the augmented matrix. The rank of the augmented matrix, in the whole matrix there are 3 non-zero rows. So rank of the augmented matrix is 3. Cover the last column and look at the remaining matrix. In that also there are 3 non-zero rows. So rank of A also is equal to 3. That's why the system is consistent, and number of unknowns is 3. So here also we will get a unique solution. And if we rewrite the system of equations, we will get x plus 4y minus 10z equal to 8. From the second equation, we will get y minus 27 by 11 z equal to 1. And last equation is z equal to 5 by 33. So starting with the last equation, if we use the method of back substitution, we will get the values of y and x. That I am going to leave as an exercise. Let's try out one more system. 4 minus 2, 6, 8 in the second. Then 15 minus 3, 9, 21 as it is in the third row. Now let's bring zeros over here. So R2 minus 4 R1 and R3 minus 15 R1 should do the trick. 1, 0, 0, 1, minus 3, minus 1. Then we have minus 2, minus 4, minus 6, 6 plus 12, 18 and 8 plus 4, 12. Then here we have minus 3, minus 15, minus 18, 9 plus 45. 9 plus 45 is 54 and 21 plus 15. 21 plus 15 is 36. Let's divide the second row by minus 6. So 1, 1, minus 3, minus 1, 0, 1, minus 3, minus 2, 0, minus 18, 54 and 36. And now to bring a 0 in the last position, 0 below that leading one, I'll have to do R3 plus 18 R2. So I'll get 1, 1, minus 3, minus 1, 0, 1, minus 3, minus 2, 0, 0, 54, minus 54, that will be 0, and 36, that also will become 0. So now look at the rank of the augmented matrix. If you look at the rank of the full matrix, there are 2 non-zero rows. So rank of the augmented matrix is 2. And after covering the last column, if you look at the rest of the matrix, still number of non-zero rows is 2. So rank of A is 2. Rank of A and rank of AB are the same. That means this system is consistent. It will definitely have a solution. But now look at the number of unknowns. There are 3 unknowns. Number of equations that we will get from here is less than the number of unknowns. So there have to be infinitely many solutions. Since the rank is less than n, n stands for the number of unknowns in the system, this system is going to have infinitely many solutions. Let's find the solutions. If we rewrite the system, we will get x plus y minus 3z equal to minus 1. From the second equation, I will get y minus 3z equal to minus 2. Now, there are 2 equations and 3 unknowns. So, one of them is going to be assigned an arbitrary value. We will call it a free variable. Now, in order to determine which one we want as a free variable, let's go back to the echelon form. This is the leading element of the first row. This is the leading element of the second row. Now see in which columns they lie. The leading elements lie in the first column and the second column. We have reserved the first column for x, second column for y. So the leading columns, the leading elements lie in the columns corresponding to the variables x and y. So we will say that x and y are leading variables. The rest is a non-leading variable. So z is a non-leading variable, and to the non-leading variable we assign an arbitrary value. That means it's free to take any value. So let z be equal to s, where s can be any real number. Now let's go to this equation. From here I'll get y is equal to minus 2 plus 3s. And from the first equation I'll get x equal to minus 1 minus y. So that will be plus 2 minus 3s plus 3z, that is plus 3s. So this cancels. X will have to be equal to 1. So the solutions that we get are x equal to 1, y equal to minus 2 plus 3s, and z equal to s. S is free to take a value. So as we keep on putting different values for s, we will get different solutions. And since s is any real number, s can take infinitely many values. That means there will be infinitely for this system. These were certain direct problems. Now let's see a slightly more difficult problem. This is a system of three equations, three unknowns x, y, z. Apart from that, we don't know the values of lambda and mu. The question in fact is to find suitable values of lambda and mu for which this system becomes inconsistent, suitable values for which it will have a unique solution, and suitable values for which the system will have infinitely many solutions. So as usual, let us start with the augmented matrix and reduce it to the echelon form. We'll take it from there. So it's 1, 1, 1, 6, 1, 2, 3, 10. 1, 2, lambda, mu. Let's reduce this to the echelon form. So R2 minus R1, R3 minus R1, 1, 1, 1, 6, 0, 1, 2, 4. This will be 0, 1, lambda minus 1, mu minus 6. Now we have got a leading one in the second row. So I need a 0 below that. So I'll have to do R3 minus R2, 1, 1, 1, 6, 0, 1, 2, 4, 0, 0. This minus this will be lambda minus 3, and this minus this will be mu minus 10. Now let us consider various cases. Suppose first lambda is equal to 3 and mu is equal to 10. Suppose lambda is equal to 3, mu is equal to 10, then lambda minus 3 will be 0 and mu minus 10 will be 0. So if we look at the augmented matrix, it will be equivalent to 1, 1, 1, 6, 0, 1, 2, 4, 0, 0. Lambda minus 3 is 0, mu minus 10 is 0. So if lambda is 3, mu is 10, our augmented matrix will reduce to this. Now look at the rank of the augmented matrix. The rank of the augmented matrix is number of non-zero rows in the echelon form. So rank is 2. Also if we cover the last column, for the remaining matrix also there are 2 non-zero rows. So rank of A is also 2. That means definitely the system is consistent, it has a solution. However, number of equations is now less than the number of unknowns. So this system will have infinitely many solutions. So this system will have infinitely many solutions in the case when lambda is 3, mu is 10. Now lambda and mu are free to take other values also. Suppose lambda is 3 and mu is anything other than 10. So now lambda minus 3 is 0, but mu minus 10 is not 0. So if I now look at the augmented matrix, first two are the same 1, 1, 1, 6, 0, 1, 2, 4, 0, 0. Lambda minus 3 is 0, but mu minus 10 is not equal to 0. Mu minus 10 is not 0. So the rank of the augmented matrix is 3 because there are 3 non-zero rows. However, if I cover the last column, then in the rest of the matrix there are only 2 non-zero rows. So rank of A is 2. So in this case, the rank of A is not the same as the rank of the augmented matrix, and that means the system is inconsistent. And finally, it is also possible that lambda is not 3. Suppose lambda is different from 3 and mu can be anything now. Mu could be equal to, I'll have to take the mu equal to 10. Suppose lambda is not equal to 3, mu is equal to 10. Then once again the augmented matrix will be 1, 1, 1, 6, 0, 1, 2, 4, 0, 0, lambda minus 3. Lambda minus 3 is now not equal to 0. In fact, I think I'll go with the initial thing itself. I will not put any conditions on mu. So, I don't really know whether this element is 0 or non-zero. I'll keep this as it is. But I know for sure that this element is not equal to 0. Now, I don't need to know the value of this element because look at the rank of the augmented matrix. In the entire matrix, this element is not 0. So, the third row is not 0. So, there are 3 non-zero rows. That means rank of the augmented matrix is 3. And when I cover the last column, still this is a non-zero element. So, there are 3 non-zero rows in A also, in the echelon form of A. And therefore, rank of A is equal to rank of AB. System is consistent and in fact, now this is equal to number of unknowns also. So this system will now have a unique solution. So this is how we analyze the various cases in order to check whether the system is consistent, inconsistent, whether it has one solution or infinitely many solutions. We now look at a homogeneous system of equations. See, we had our linear system of equations a11 x1, a12 x2 plus a1n xn equal to b1, a21 x1 plus a22 x2 plus a2n xn equal to b2, am1 x1 plus am2 x2 plus amn xn equal to bn. So this was our general system of n equations in n unknowns. If it so happens that all the constants on the right hand side are zeros, if all the constants on the right hand side are zeros, such a system will be called a homogeneous system. And in matrix form, this system will look like Ax equal to capital A. Now, for a homogeneous system, no matter how complicated the system may be, I can straight away give you one solution. If I put x1 equal to 0, x2 equal to 0, xn equal to 0, all equations are going to be satisfied no matter what values the coefficients take. So, for a homogeneous system, x1 equal to 0, x2 equal to 0, x1 equal to 0 will always be a solution. That's why we call it a trivial solution. Nothing very great about it. This solution will always be there associated with a homogeneous system. So one thing is clear. For a homogeneous system, we never get the case that the system is inconsistent. It will never happen that this system does not have a solution, because the solution is always there. So for a homogeneous system, only two things can happen. It can have either only one solution, in which case it has to be the trivial solution, or it will have infinitely many solutions. Trivial solution will always be there, but in addition to this, it can have infinitely many solutions. So for a homogeneous system, there are only two possibilities. There is only the trivial solution, unique solution case, or there are infinitely many solutions. The method, of course, for solving a homogeneous system remains the same. So let's try out the problem of the homogeneous type. Solve the system x plus y minus 2z plus 3w equal to 0, x minus 2y plus z minus w equal to 0, 4x plus y minus 5z plus 8w equal to 0, 5x minus 7y plus 2z minus w equal to 0. Now, this is a homogeneous system. Like we do for a linear system, you can take the augmented matrix, reduce it to the echelon form and proceed in a similar manner. But for a homogeneous system, it's not really necessary to take the augmented matrix, because in the augmented matrix, the last column will contain only zeros, and no matter what transformations you perform, these zeros are not going to be affected. So till the end, this column of zeros is going to remain as it is. That's why if it's a homogeneous system, you don't really have to take the augmented matrix. You can just take the coefficient matrix and solve it from there. So let's look at the coefficient matrix. Here, rather than waste time on computing the echelon form, I'll directly give you the echelon form. You can verify the echelon form later. Of course, I must warn you that the echelon form is not unique, because once again it all depends on the sequence that you use. But I've done enough problems, so by now you know how I think. So if you follow my sequence, then this is the echelon form that you will get. In any case, even if your echelon form is different, the conclusion has to be the same. So the echelon form that I get is now look at the rank of the coefficient matrix. Rank of the coefficient matrix is 2, and number of unknowns is 4. So number of equations is less than the number of unknowns. If that happens, the system has infinitely many solutions, and 2 of the variables now, because the difference is 2, so 2 of the variables will be free variables. So let me rewrite the system of equations. It will be x plus y minus 2z equal to 3, y minus z equal to 4 by 3. No, I'm sorry. We are dealing with a homogeneous system of equations. First column is for x, second is for y, third is for z, last is for w. So it will be x plus y minus 2z plus 3w. And constants, as I mentioned, they are not going to change, they will remain 0 throughout. So on this side I get 0. Second equation is y minus z plus 4 by 3w equal to 0. And now let's determine which are the leading variables. So look at the leading elements in the non-zero rows. They again fall in the first and the second column. That means x and y are the leading variables. So z and w are the non-leading variables. So to these non-leading variables, I'll assign arbitrary values, and when I substitute for y, z and w, I'll get x also in terms of s and t. And as s and t take different values, we'll get different solutions for this homogeneous system, and in this case, we get infinitely many solutions. The last problem for today has to do with a square matrix. Let us see what happens if the coefficient matrix is a square matrix. Let me give you all the problem first. Show that the system of equations 2x1 minus 2x2 plus x3 equal to lambda x1, 2x1 minus 3x2 plus 2x3 equal to lambda x2, minus x1 plus 2x2 equal to lambda x3 can possess a non-trivial solution, if and only if lambda is 1 or minus 3. Now, in this form, at the first glance it may look like it is not a homogeneous system, but let me readjust the terms. See, on the right hand side I am having unknowns, so I must transfer them to the left hand side, and if I transfer them and rewrite the system, it is going to look like 2 minus lambda times x1 minus 2x2 plus x3 equal to 0. Second equation will be 2x1 minus of 3 plus lambda x2 plus 2x3 equal to 0. And last equation will be minus x1 plus 2x2 minus lambda x3 equal to 0. Now there is no doubt that this is a homogeneous system of equations, and we are only interested in finding out when this system will have a non-trivial solution. Now fortunately over here there are 3 equations and 3 unknowns. So the coefficient matrix is going to turn out to be a square matrix. It will have 3 rows and 3 columns. And the result is, suppose I have a homogeneous system in which this is a square matrix of order n, then this system has a non-trivial solution. This system has a non-trivial solution if and only if determinant of A is equal to 0. That means the matrix is singular. So, since this is a square matrix, I can make use of this result. Then I don't really have to use row reduction. That method is always there. But I could use this determinant method to find the values of lambda. So, this homogeneous system will have non-trivial solutions if and only if determinant of the coefficient matrix has to be 0. If we expand this determinant, we will get a polynomial in lambda. I have done the calculations. We get lambda cube plus lambda square minus 5 lambda plus 3 equal to 0. Now if you all have done the equations, polynomial equations of degree 3 first, well and good. If not, then let me tell you how to get the roots from here. The first root is to be got by trial and error. So you have to keep trying lambda equal to 1, lambda equal to 2, lambda equal to 3 till something works. Now here fortunately when I put lambda equal to 1 itself, if I put lambda equal to 1, I will get 1 plus 1 minus 5 plus 3 which is 0. So lambda equal to 1 is going to be 1 root. And then use the method of synthetic division. The other factor that we get is lambda square plus 2 lambda minus 3 equal to 0, and when I factorize this, I get lambda minus 1 into lambda plus 3 equal to 0. That means lambda is 1 or lambda is minus 3. So the 3 roots of this equation are 1 because 1 is repeated and minus 3. That's why this homogeneous system will have a non-trivial solution if lambda is 1 or minus 3. That's all.